Okay, everyone, we're going to get started. So my name is Aaron Stannard. I'm the CEO of Petabridge. I'm one of the contributors to Akka.NET. And today we're going to talk about real-time distributed applications with Akka.NET, Kubernetes, and .NET Core. Now, before I begin, quick show of hands. Who here has worked with Akka.NET before? All right, a handful of you. Good. This talk is intended for people who are interested in learning about using Akka.NET to build these types of systems we're going to talk about today. So I'm not going to assume you have that much familiarity with it. Now, next question I have is who's used Kubernetes before? Quick show of hands there as well. Okay, about half the room roughly. The purpose of this talk isn't to necessarily hold your hand and give you step-by-step instructions on how to do all of these. I'll provide you with the link at the very end for a place where you can go do that. What this talk is really about is trying to give you a strategy for how to build a real-time application using technologies like Akka.NET and Kubernetes to do it. So real-time applications are becoming increasingly common in the workplace. Whether you work in consumer or whether you build enterprise applications, there's lots of different business cases, like the ones I have behind me on screen, where real-time application programming is becoming necessary. And the reason why we have to do this is because the market demands it. Users want to receive notifications when they have a bill that's past due. Enterprise users want to know what the real-time position of each of the vehicles in their fleet of ships or their fleet of trucks are at any given time. And in order to support these types of business cases, engineers like you have to be able to deliver real-time software experiences to the stakeholders in your organizations. Now, what makes an application real-time? Well, I'm going to go ahead and break it down into three sort of simple ingredients for you. The first thing that makes an application real-time is you have a soft processing deadline that every single request must fulfill. So a good example is if you're building, let's say, a real-time threat monitoring system or fraud monitoring system, you might be told you have to figure out whether this transaction is legitimate or fraudulent within 1.5 seconds of the transaction being posted. That's an example of a soft real-time deadline. If you end up delivering it in 1.6 seconds, that's not great, and that impacts the business's throughput, but it's not a mission-critical failure like how it would be in a hard real-time application. A hard real-time application being something like the braking system on your car, where if you don't brake at exactly 20 milliseconds, the passenger might die. So that's the distinction between hard and soft real-time. We're talking about soft real-time in today's course. Now, the next requirement that makes your application real-time is a non-trivial workload. So for instance, if you went ahead and created, let's say, a static website using GitHub pages and Jekyll or something like that, that's not a real-time application, even though it might be really fast, because the workload is completely trivial. It's stateless, in fact. And that's the third criteria that usually determines whether an application is real-time or not. It's performing stateful activity. So to give you a good example, if you're building something like a monitoring system, typically you have to keep a sliding window of state about the prior performance of the system. So you might need to know, what's the error rate been on this application I'm monitoring over the past 30 minutes? And what's the error rate also been over the past minute or so? And you might want to go and compare how the current minute compares to the previous 30. And when there's when the two curves pass each other of the error rate, you might have to go and fire an alert to some of the end users who are responsible for monitoring that application. That's an example of what a real-time application looks like. And increasingly, more and more developers are being asked to build applications like this. Now, the first question I want to address that you might have is, why is statefulness a criteria to build a real-time system? Well, I want to give you two architectures on the screen behind me here. On the left, you have a traditional CRUD architecture, where every single time a request comes in, we go ahead and turn that into a database query. We serialize that query over the network. We go ahead and execute that query on our database engine. We serialize the results from the engine, send that back across the wire, transform those database engine results back into a response, and then serialize that and send that out over the wire. That's what traditional CRUD workloads look like. Well, compare that to the workload on the right, where we're taking advantage of a principle known as state locality, where all of the information we need to do the work is available adjacent in memory to the code doing the work. So in that use case, we receive the request, we go ahead and access an object that's already available in memory and serve up a result right away. The performance difference between these two systems is multiple orders of magnitude, and it's because we're operating at a very high level of I/O. So in order to build applications that can execute in real time, we often need to take advantage of state locality in order to do it. That's why statefulness is a core ingredient for building real-time applications. And the majority of what this talk is really about is once you start having to manage state inside your application, you as a developer become responsible for a whole bunch of new complexities that you weren't responsible for under the old stateless CRUD model. But don't worry, we're going to offer a strategy that'll help you manage that. So the big challenges with building real-time applications is that you're responsible for managing the consistency of your state. This used to be something that SQL Server or Cosmos DB or Azure Table Storage might have taken care of for you. Now you have to do it because your state and the source of truth lives inside your application. On top of that, now you're responsible for migrating state from one node to another during deployments, during upgrades, and also during failure scenarios, or maybe some of the hardware inside your cluster fails and you have to move that critical state from one area of the cluster to another. This can be a non-trivial problem, especially when you have to manage the consistency of it too. And then finally, most deployment tools that we've used historically as developers are not equipped to deal with state. They're used to working with stateless web servers. So the idea that you might need to replace nodes one at a time because state needs some time to move from node A to node B during a deployment is not something that most deployment engines are equipped to handle. That's why we're going to be using Kubernetes today. It's one of the very few tools that has a natural built-in way of expressing that idea rather easily for a developer. So here's the roadmap of the tools that we're going to use, how we're going to connect them together, and how they can solve these problems that I showed you on the previous slide. The font might be a little small, so I'm going to go ahead and read this for you. The first thing we need to do is create a workable model for managing individual entities consistently, each individual thing we're responsible for. So if we're monitoring, let's say we're a multi-tenant monitoring application, we need to come up with a way to monitor each tenant inside of it individually and make sure that all that data for each tenant is managed consistently on its own. Next, we have to have a mechanism for routing events and state to those specific entity actors inside our system. If we have a big distributed network of nodes that can all have state on them, how can we make sure all the state for the same entity ends up being made consistent at the end of the day? That's the next thing we're going to have to address. And then we're going to need to talk about topology awareness inside the network. How do I know which state is on which machine? And when one machine needs to restart or be redeployed, how can I move that state from point A to point B in a manner that obeys our consistency principles? Then after that, we need to come up with a deployment mechanism for being able to go and deploy into these stateful environments. We don't want to go ahead and rip all of our stateful nodes all out at the same time and then replace them all at once, like how you might do with a VIP swap if you're using a web server. That would cause some consistency problems if we did it that way. So we need a deployment strategy that allows us to go ahead and replace the nodes one at a time, providing each node with enough time to hand over its state to the next node that's still available inside the network. And then we need to put everything together. AkkaNET is going to help us with the first three steps of the puzzle here, and that's honestly the hardest part. Using AkkaNET as the building blocks to give our programmers and our DevOps people a workable model for managing all of this inside our environments. And Kubernetes will take care of the latter parts. Kubernetes has a tool built inside of it called a stateful set that does these very things we're discussing automatically. So we're going to use Docker and .NET Core to deploy our AkkaNET applications in a stateful manner using Kubernetes. That's the overall goal. But the first thing we're going to learn about is how can we go ahead and use AkkaNET to manage these stateful environments inside our system. So a quick show of hands, who's worked with actor programming before, period? Whether it's Erlang, Akka, Okay, good. I'd say about a third of the room or so. Actors are simple, standalone entities that communicate by processing and sending messages to each other. So this is all locally inside one process, what I'm visualizing on screen here. Actor 1 receives a message from somewhere. It could be another actor. It could also be from an external process like a web API or Kafka or maybe Azure Event Hubs, whatever you want. That message arrives into Actor 1, and Actor 1 wakes up and gets scheduled on the .NET thread pool to go ahead and process some messages under the covers. And the actor will process a burst of up to 30 messages by default before it yields the thread and lets another actor take a turn behind it. Well, Actor 1 can send a message to Actor 2, and that'll cause Actor 2 to wake up and process some messages. All of this is done asynchronously, and the big implication here is that actors, when they don't have messages to process, don't use CPU. Actors only do work when there's something for them to process inside their mailbox. And an actor's mailbox is just a simple first in, first out queue, is all that it is by default. Now, this is a little bit of actor code on screen here. And basically what you can see is an actor is just a simple class, is all that it is. There's no special infrastructure or anything else that you have to manage as a developer. You create an actor class, and then what you can do is declare these receive methods here, where you can go ahead and see, I want to receive a message of type attempt crawl. Whenever an actor receives a message of that type, we will execute the method that we've declared in there. That Lambda method is the code this actor is going to run. So the actor will process a little bit of code, and then by the time it's done processing this message, it'll yield the thread to either another actor that's got some work to do, or if this actor has even more messages it needs to process, it'll move on to processing the next one. So we're not going to be showing, by the way, a tremendous amount of code in this presentation. This is really about trying to provide you with the roadmap for solving this type of complex problem. The link I'm going to provide you with at the end will give you a sort of a step-by-step, do-it-yourself tutorial you can follow to learn how to do this on your own. Now, the next ingredient we need to talk about with actors is how do we actually send them a message? The code I just showed you is how they process them, but how do we actually get a message into them in the first place? And that's what this unit of work called the actor reference does. The actor reference is like a handle for talking to an actor. I go ahead and I create an actor system initially. An actor system is sort of the environment that hosts the actors. It's what allows them to communicate with each other. It provides each actor with a unique address and is responsible for creating things like the actor's mailbox that it uses for processing messages. Down below that, you can see we go ahead and declare some props. Props is the formula we use for starting an actor. If an actor crashes and needs to restart, it'll be recreated using the very same props that were used to create it in the first place. Now, I'm a little embarrassed to admit this, but I had worked on Akka.NET for close to 2 years before I figured out that the reason why this is called props is because actors need props on stage in order to act. So, sorry, that was a terrible joke. Now, the last thing you'll see in the sort of the third step here is we get an actor reference by calling the actor of method on the actor system, and we pass in that props along with a name for that actor. Now, the name is optional. If you don't pass in a name, Akka.NET will assign a random one for you. So I get that actor reference back, and now that's how I can communicate with the underlying actor if I want. And that's what I do in the final stage here. I tell the actor this greet message saying, hey, I want you to go ahead and process this. And by the way, every time you send a message to an actor via a tell command, that is always asynchronous. The message will get queued into the actor's mailbox, and the actor will get woken up later to go and process it. Akka.NET actors use fire and forget messaging by default, and that's what you're seeing right there. So this is kind of the basis of how we go and set up actors. Now, actor references are really important for another reason, which is that when we start doing networked actors using Akka.remote and Akka.cluster, actor references have a very useful property that we're going to leverage to build a distributed system. And that property is called location transparency. I can tell this message to an actor running locally inside the same process as this actor system, or I could also tell a message to an actor running in a remote process somewhere else inside our data center. And as a programmer, that's 100% transparent to you. You don't need to know where the actor is on the network or necessarily what its implementation type is. All you need to know is this actor can handle this type of message, and it'll send me 0 to n responses back based on whatever the actor's state is and other sort of factors that can occur inside the system. So location transparency with actor references is one of the little building blocks we can use to build a distributed system. Now, the whole reason why I've been bringing this up is we're really talking about how we manage state inside a real-time application. Well, actors have some very useful properties that make them ideal for managing state. The first important property is that actors are serial processors. They process messages in the order in which they were received and process them one at a time. So if we have a queue of 3 messages sitting in our actor's mailbox, message 0 will get pushed into the actor's receive method, that code we saw a few slides ago. The actor will go and process that, and once that receive method exits, the actor will move on to processing the next message in the mailbox, message 1. So one of the implications here of the fact that actors are serial processors means that any state that is held inside an actor, and by the way, the state inside an actor is literally just fields and properties, just like you'd have in any other object in .NET. But the state inside that actor can only be mutated in a sort of single-threaded, non-concurrent fashion, which means that the actor's state is always consistent with whatever messages it's received. You don't need to have any complex synchronization mechanisms or anything else. The actor's mailbox provides the ordering to guarantee that that state can only be modified linearly, which is one of the highest modes of consistency. Now, on top of that, actors are cheap resources. An actor in AkkaNET takes about roughly 1K of memory and doesn't use any CPU when it's not running. And we can spawn up to 50,000 actors per second using our standard benchmarking machine, which is a D2V2 Windows Azure VM. It's a 2-core VM. So actors are cheap resources. We can afford to have many of them inside a single process. So one of the implications of this is that if we have an actor hierarchy, which is how actors get organized inside Akka.NET, you have parent and child actors. It means that we can use this actor hierarchy inside actors to partition our state. Meaning, in an environment where, let's say you're responsible for tracking an arbitrarily large number of entities in real time in your system at any given time. Well, one of the techniques you would have probably used without something like Akka.NET would be a giant sort of cached in-memory collection inside each process. And you might try to synchronize that by having a copy of that cache saved to some central location like a Redis database and so forth. And that can get very nasty very quickly. I've done it before myself, so I've been there. I've made those same mistakes. What the Akka.NET sort of actor model allows you to do is rather than worrying about having this sort of global mutable state that everyone's trying to synchronize, we go ahead and concentrate our state for every business entity inside a single actor who has exclusive ownership over it. So one actor per entity is sort of the standard pattern that you see throughout a lot of actor programming. So to give you a little historical example, the last business that I ran prior to starting Petabridge was a marketing automation company for Windows App Store developers called Marked Up. And we used Akka.NET. We were the very first production Akka.NET user. We use Akka.NET actors to keep track of the click streams of all the users using our customers' applications in the store. And we needed to figure out, did this user qualify for a campaign that this user might be running, this app developer might be running? As soon as the user, let's say, tries to buy an in-app purchase and then backs out, we could go ahead and target them and send a push notification offering them a discount on that very thing they were looking to buy. In order for our application to be effective, we had to be able to guarantee that the time between that user triggering that campaign and receiving that notification had to be about a second. Otherwise, our conversion rate for our customers would drop by about 40%. This is a good example of a real-time application. The way we made that work so our engineers could manage all the complexity of doing this was we partitioned the campaign state for every user inside its own actor. So the child per entity pattern gives you a simple model for being able to make sure that every single entity inside your system is modified in a consistent and understandable manner. This is a very intuitive way of trying to go and manage state inside your application. Partition each individual entity into its own actor, and therefore each entity's state can be modified serially, which makes consistency a much easier thing to come by than it is in sort of the concurrent, shared state, anything goes universe that we're used to operating in. So this is the first really big linchpin of trying to build stateful applications. Now, to summarize here, actors simplify stateful application programming by doing the following 4 things. They process messages serially, which means that every single change to your entity state occurs linearly. That's the first big change. The second is that all actor state is private. State can only be modified by passing immutable messages between actors, meaning that an actor's state can only change atomically inside its own sort of private area. If another actor wants a copy of your state, you go ahead and copy your state into a message and send it to that actor. So that actor will go ahead and get a point-in-time snapshot of what your state looked like. Now, if you want to go ahead and have an actor synchronize with another one, the way you do that would be through using something like publish and subscribe, where every time an actor's state updates, it publishes those copies out to someone else inside the network. It's a very common pattern in AkkaNET. On top of that, the actor hierarchy itself is a very useful tool for partitioning state, where each entity gets its own actor, and all those entities can be updated concurrently if you want to, which is what helps make actors very high throughput, which is one of the things that we need for doing real-time applications. And then finally, the most important tool is the fact that actor references are transparent. They can be spread throughout the cluster, and many different nodes in the cluster can all send messages to the same entity actor, which allows us to build a consistent view of that entity in a single place inside the cluster. Now, the second part of the puzzle is how do we make sure that happens? How can we make sure all those events all get routed to a single place inside our cluster? What's the magic trick for pulling this off? Well, the trick is a couple of other modules that are part of the AkkaNET framework, namely AkkaNET Cluster and AkkaNET Persistence are going to be some tools we look at. So this is what an AkkaNET cluster looks like. Each one of these circles here represents an actor system. That's the sort of hosting environment we use to go and create actors. And typically, in a Kubernetes environment, each one of these actor systems is going to be its own Docker container. So one container equals one process equals one actor system. That's the most granular way of trying to manage an AkkaNET cluster. Each one of these nodes is its own actor system, and all of these nodes are connected via TCP connections to all of the other nodes. And they're able to send messages back and forth between each other's actors transparently. All of the serialization and routing is handled automatically by the AkkaNET framework itself. So you as the developer don't need to worry about whether you're sending a message to a local actor or a remote one. The framework will make that transparent for you. Now, in terms of what AkkaNET Cluster does, so we're not going to get into a gigantic amount of detail, but to give you just enough information so you can start researching it on your own. AkkaNET Cluster is fundamentally about building peer-to-peer networks in a server-side, back-end environment. AkkaNET Cluster allows us to discover new nodes automatically and remove old nodes that need to be updated. Or in the case of a sudden network partition, we can detect when a node that was on the network becomes unavailable and stop routing work to it until it becomes available again. We don't want to send messages across a bridge to nowhere, right? Now, one question you might be asking, why would I want a peer-to-peer network in a server-side environment? Why is that a remotely useful thing to me? Well, the answer is peer-to-peer networks are increasingly a good tool for trying to guarantee high availability inside a distributed system. The reason is, I'll move on to the next slide for just a second here. The reason why peer-to-peer networks are helpful is they're decentralized. There's not a single master that dictates what the total state of the system is at any given time. Rather, that state is distributed across the edges of the system in a peer-to-peer network. And one of the profound implications of this is is that this helps us avoid single points of failure and single points of bottleneck. If one node goes down in our peer-to-peer network, we lose some of the bandwidth and capacity that node had, but it doesn't compromise the total availability of the system. We're able to stay available and continue processing requests. So that's why we want to use a peer-to-peer network here. It's one of the tools that can guarantee that we can go and scale out in a linear fashion. If you double the number of nodes in a peer-to-peer network, you double its capacity, right? That's not necessarily true in client-server networks, where the server that's sort of the root dependency, typically your database server, can't scale linearly. That's always the bottleneck that constrains the growth of the system. This is not the case in a stateful peer-to-peer application like the type you can build with AkkaNET Cluster. Now, last thing I wanted to mention is that a couple of the other important features AkkaNET Cluster has. One feature that's quite useful is called roles. These are tags or labels you can apply to each node inside your cluster. This allows you to build a heterogeneous application where there can be different services that all work cooperatively together inside the peer-to-peer network that do different things. The sample application that I'm going to try to get to has a total of 4 different services running inside of it that all perform different workloads fundamentally. And they're all able to work cooperatively together, and they might even be written by different teams within your organization. As long as they all have standardized messaging contracts, that can work. So that's what roles are all about. And then the last feature that AkkaNET Cluster itself ships is what's called a clustered router, which is an actor that can detect when new nodes join the cluster and when old nodes leave, or when nodes become temporarily unavailable, and can route messages to the appropriate party based on who's inside the network right now. And that's the tool we're going to look at today for doing state distribution inside our system. Now, the way a cluster forms, I'm going to go ahead and skip through some of this real quickly because in the interest of time here. But the way a cluster forms is you have at least 2 nodes that exist on sort of a well-known address, maybe even a static address inside your network. And they act as the seed nodes that help form the basis of your cluster. Well, when the rest of the nodes start up inside AkkaNET Cluster, they're all configured to go ahead and communicate with those seed nodes initially. And after a period of time, every node in the cluster will be connected directly to every other node. This forms a specific type of peer-to-peer network known as a mesh network, where every node is directly connected to every other node. This means that nodes don't have to worry about doing traffic routing and load balancing, because they all have their own connection to each party. And it also means that failure detection inside a mesh network is pretty close to real time. If one node crashes, every other node knows that their connection to it was broken within a very brief window of time here. So since we're interested in building real-time applications, being notified immediately about failures inside our system is quite important. That's why a mesh network design like this works pretty well in our favor. Now, we're going through a lot of concepts, so I'm going to put these slides online and be available for questions afterwards. But the next thing I want to introduce is probably one of the most important concepts in not just Akka.NET, but distributed programming in general, which is how can you partition and distribute state in an intelligible fashion inside a network like the types you can build with AkkaNET Cluster. The technique we're going to look at primarily is known as consistent hash distributions. Or in Akka.NET, we're going to use a specific type of router called a consistent hashing router. This is an actor that uses a consistent hashing strategy to figure out all the entities for a specific hash key should all go to the same place inside the network. That way I can build a consistent picture of what that entity state should look like. So we're going to use that. But some other techniques that are available inside AkkaNET Cluster for distributing state. AkkaNET Cluster sharding is probably the tool that most people use in production. It's a little bit more intelligent than a consistent hash router, but it uses the same math under the covers. And then finally, if you saw Bartosz's talk a little bit earlier today on CRDTs, there's another module in Akka.NET for doing in-memory replication called distributed data. So Bartosz gave his talk a little bit earlier today. He's here in the front row if you want to ask him about it. But that's yet another way of distributing state inside Akka.NET that we're not going to touch on today. Our strategy for trying to guarantee consistency inside an AkkaNET Cluster application is we're going to try to guarantee there is exactly at most one instance of an entity actor inside our system at any given time. If we started allowing, let's say, at least one instance of an actor, where if a node went down inside the network, or excuse me, if a node became unavailable inside the network and we immediately tried to move that state to another node without knowing if that process had shut down, that would violate some of our consistency rules. And you'll see an example of that in just a minute. But this is our strategy for trying to manage state consistently inside our system. Now, the way a clustered router works in AkkaNET is, let's suppose we have 4 nodes that are all identical. They all run the exact same code. They're all going to work cooperatively together to try to give us some scale and some fault tolerance to solve these sort of real-time state processing problems that we have. We're going to create a router on one of these nodes. When nodes 2 and 4 are able to connect to node 1 and form a cluster, that router will begin adding entries into its routing table for each one of those nodes, which will allow us to begin distributing messages to either one of those nodes. So as soon as that router, a node number 1, because a router is just an actor, as soon as it receives a message, it'll be able to go and forward that message to the appropriate node based on its routing strategy. That strategy could be a round-robin strategy. It could be a broadcast strategy where every node gets every message. But the one we're going to focus on today is called a consistent hashing strategy. And by the way, if node 4 becomes unavailable, the router will typically stop sending messages to that node until it comes back again. Now, what I really wanted to talk about in the context of distributing state is a mathematical technique called consistent hashing. This is used in databases for partitioning keys. It's used in caches like mcached for being able to make sure that each cached object is unique inside the system. And we use it inside AkkaNET, both inside clustered consistent hashing routers and inside cluster sharding. And the way this technique works is you take a consistent hashing function. So MD5 and Murmur3 are examples of them. And what makes a hash function consistent is the fact that the same input always produces the same output each time. So that means every node in the cluster, when they hash the same key, always get the same output back. Now you might be thinking, doesn't every hash function do this? And the answer is no. A good example of a hash function that does not do this is anytime you call get hash code on an object in .NET. Those hash codes are all slightly randomized from process to process. And that's in order to prevent a specific type of attack called a hash code prediction attack. So that's why hash codes from the normal .NET base class aren't reliable for doing this type of distribution. We have to go and run our keys through something like a MD5 or Murmur3 algorithm instead. Now, the other thing that makes consistent hashing functions interesting is their hash range can be plotted linearly in a circle. In this case, a clockwise circle. We're going to assume that our hash output is an unsigned long integer for the sake of making it simpler. And so that means we have 2 to the 64 possible hash values that can ever be output from this function. Well, I can go ahead and carve up that hash range into pie slices, where node 1 owns the first pie slice, node 2 owns the second, node 3 owns the third, and you get the idea, right? We can redivide this pie however many times we need, depending upon how many nodes there are inside our network that can host this type of entity. So the big implication here is, oops, sorry about that. The big implication here is that if I go ahead and send 2 messages to my consistent hash router, for both of them have the hash key Aaron as their key value. Well, that means that I know that those hashed values are both going to go to node number 1. And if I go and input a totally different hash key, let's say a GUID of some kind, I know that that message will be routed to node number 2 instead of node number 1. So inside our network, if I go ahead and send a message of type Aaron to one of my consistent hash routers, I know that that actor that owns that entity exists on node number 3, because that's where the hash value was placed on the ring. So I'm going to go ahead and route that message to node number 3. If node number 4 receives another hash key, another message with a hash key of Aaron, I'm going to route that to the exact same destination actor on the other side of the network. and so on. You get the idea. What this means is that we're able to form a complete picture of what this entity state must look like inside this actor running on node number 3 inside our network. This helps us form that consistent view we need in order to build these real-time applications that can work effectively. So that's the state distribution piece. Now we need to worry about one of the other complexities that state introduces inside our application, which is state has to be moved when the topology of our cluster changes. So let's say we have these two web nodes talking to a business node under the covers, and we need to upgrade this node with an updated version of our application. Well, what's going to happen is we might bring that new node online, and we have to suddenly move that state from all the actors that were running on the old node onto the new one. And this is where some tricky consistency issues can happen. How do I make sure the data that our entities saved on the previous node properly gets moved onto the new node that we just started up? How can I make sure that happens? Well, the most common technique for doing this is using a technique called AkkaNET persistence, which uses event sourcing under the covers. The way this works is, as an actor processes events that cause it to change its state, we persist those events, or we can even persist a snapshot of what our state looks like to a durable store like a database or a cloud file system, or any number of other sort of durable mechanisms. 99% of the time, it's going to be a database, though. What this means is that when an actor is moved from one node in our network to another, that actor can go ahead and begin replaying the events it persisted, and it can use that to rebuild its state. And AkkaNET persistence is able to guarantee, by the way, that that actor will fully recover its previous state before it can begin processing any new messages. That's how we can make sure that that data is consistent from one node to another inside the network. Now, if I'm using a clustered router as my primary tool for distributing state, here's what this whole picture put together looks like inside AkkaNET cluster. So we have a clustered consistent hash router on one node routing events to a stateful service that's operating on another node inside the network. Well, what will end up happening is if I bring a new node online, and I go ahead and I distribute messages still to this router, and that router gets a notification that this new node is available. What I'm going to go ahead and do is say, okay, I want to begin routing messages for some of those entities to this new node that is now here. I've redivided that hash range in half. Well, what will end up happening is we'll recreate this new entity actor underneath the routee that's on the other end of the router. And it'll begin recovering its state from the database. And once it's done that, it'll go ahead and start updating its state and processing events just like how the old incarnation of that actor did, which we can now safely pull offline. Now, you might be wondering, if you take a look at this graph, if I go back to this stage, this looks a little dangerous, doesn't it? We have an actor recovering its state while there's another incarnation of that same entity actor running in a different place in the network. This is effectively a type of potential consistency problem known as a split brain. This is what AkkaNET cluster sharding can help solve. It's able to guarantee that before we create the new actor, we passivate and terminate the old one before moving it onto a new node. Now, this talk already introduces enough new concepts, so I decided to leave cluster sharding as homework for you to explore on your own. But it essentially uses the same type of math and distribution mechanism. It's just able to buffer any messages that would have gone to the new entity actor until the old entity actor has been terminated. That's why cluster sharding is the preferred mechanism for doing this in production. I'll go ahead and move on here. Now, these are all the different pieces that you, as the application developer, need to be concerned with while you're working with Akka.NET. Kubernetes is the next piece of the puzzle, and it won't take too long. But we're going to go ahead and talk about how we can use that to do continuous deployments of this application without having to lose state or worry about consistency. And if I have enough time at the end, I'll go ahead and do a live deployment of one of my own Kubernetes clusters that I just set up specifically for you guys. So why Kubernetes? Well, it looked like about half the room is already using it, so The first point, that it's ubiquitous, appears to be true. But the reason why I tend to lean towards Kubernetes for my applications is because it's one of the only tools out there that has a really good first-party concept for how to manage stateful applications. Docker Swarm, by contrast, does not have a mechanism like that. So that's one of the sort of weaknesses of some of the other orchestration platforms out there. But on top of that, Kubernetes has a really rich ecosystem built around it. You're going to see in a minute here that I'm using Azure Kubernetes Service, but Amazon and Google also have their own Kubernetes services that they offer to developers. And on top of that, there's got to be at least a dozen turnkey Kubernetes vendors for building on-premise systems too. So if you work in healthcare or finance or government or defense or whatever, there's plenty of different options you can use to make sure Kubernetes works in an environment that suits you and your organization's needs. Now, as for why Azure Kubernetes Service, the long story short is it's probably the easiest one of these environments to set up. That can actually give you a little bit of scale. It only took me a few minutes to do it right before this talk. So I recommend that as sort of a set of training wheels for learning how Kubernetes works. Now, a couple of core concepts in Kubernetes. Kubernetes is fundamentally an orchestration platform. What it's designed to do is if you have multiple host machines that can all run Docker containers that house your application and maybe some of the other pieces of infrastructure you might need, like monitoring or tracing tools, Kubernetes abstracts the fact that there might be many pieces of hardware all involved in trying to service those requests. It gives you sort of a flat surface you can deploy onto. And Kubernetes will figure out on which boxes should each application be deployed. And it tries to do that to guarantee the maximum degree of fault tolerance and availability inside your system. So for instance, if you deploy 3 replicas of one of your applications, Kubernetes will spread that out across multiple hosts rather than clump them all together on a single box. And then lastly, Kubernetes is highly configurable. You can go ahead and, for instance, specify that when an application needs to be restarted or deployed, you can go ahead and say, you know what? I actually want you to add a brand new instance of this node before you begin replacing the older nodes. Give me some more headroom rather than replacing existing nodes right away. It has a lot of different knobs and dials you can use to configure your deployments. And that's really useful in environments where you have a large amount of traffic. You want to go ahead and make sure you have enough buffer room that in the event you start doing a deployment, you don't lose some of the capacity you need to stay available. And this is fundamentally what sort of a Kubernetes deployment might look like in production. You might have, let's say, 3 hosts, 3 different machines, all running the Kubernetes agents on it. And they're the ones managing the Kubernetes pods, which are the little units that house your Docker containers. And most Kubernetes services will be totally hidden from the network. Akka.remote and Akka.cluster, for instance, should never be publicly exposed over the network directly. Instead, you might want to go ahead and expose your Kubernetes service through the public endpoints you define on something like a web browser or RabbitMQ ingestion service. Any number of different tools that can provide you with robust security and authorization mechanisms. Akka.cluster is just infrastructure. It's not meant to provide all that for you. It's meant to get messages very rapidly from point A to point B. This is fundamentally what a deployed sort of Kubernetes architecture might look like. And in our case, we're just exposing a load balancer service to do some round-robin load balancing around our web application, which is what feeds data into this particular application I built. And then on Azure AKS, I took a screenshot here of what all the fully provisioned infrastructure looks like in Azure. In fact, one thing I'm going to do real quickly here is I'm going to change my screen. Just a second here. That looks beautiful, doesn't it? All right, give me just a moment. Okay. Now, what I'm going to go ahead and do real briefly is I'm going to pull up my live running cluster here. I think I need to wrap it. There we go. Here we go. So if I take a look here on screen, this is what my live running Kubernetes cluster looks like. It's literally just this little clump of stuff right here. But under the covers, what that AKS cluster really is what you see in my presentation if I go back. It's a series of disks and virtual machines and a network and security groups. Azure goes and creates all that infrastructure for you under the covers, so you don't have to figure out how to do this on your own. If I had to go and build an environment like this on my own, probably would have taken me like 2 weeks to do it. Instead, with Azure Kubernetes Service, I can get this spun up in a matter of minutes instead. That's why I strongly encourage you, if you're looking to learn how Kubernetes works, AKS is a really good way to get started. Now, some key terms for Kubernetes in the context of AkkaNET. First is a pod. A pod represents a single unit of work inside Kubernetes, and typically one pod houses one Docker container. It's technically possible for multiple containers to run inside one pod. So for instance, if you're using AkkaNET and New Relic, and you want to use New Relic for monitoring, you might deploy New Relic as a sidecar Docker container inside your pod. Although that's kind of unusual though. The really big term that we want to remember as AkkaNET developers is a stateful set. That's the mechanism we're going to use for deploying AkkaNET services to Kubernetes. Because stateful sets are identified as Kubernetes as nodes that have to migrate state from point A to point B. So typically what Kubernetes will do during a deployment against a stateful set is they'll go ahead and rotate your nodes out one at a time, and they'll provide a long grace period for changing those nodes too. And then lastly, we have the concept of a service. A service is how you go and expose your pods inside the network, inside Kubernetes. So some services can be exposed publicly, like a load balancer or an ingress service. Most services inside AkkaNET are headless, meaning they can only be accessed inside the Kubernetes environment. So in the case of our little sample here, in fact, you know what? Let me go ahead and get my mouse out. All of these the containers here contain AkkaNET services, and they're all networked together inside the Kubernetes network. The only pods that are exposed directly to the outside is the service that houses our web pods. It goes and allows us to route traffic on port 80 to the ASP.NET Core process that I set up. In a stateful set, if I want to do a deployment, what will end up happening is I'll go ahead and tell Kubernetes, I want you to change the version of the Docker image that's currently running inside here. I want you to move from image number 0.24 to 0.25. And that's going to be what triggers the deployment inside Kubernetes. So what Kubernetes will do is it'll go ahead and kill this first container. It'll say, okay, I'm going to have you gracefully shut down. And it'll give it enough time to hand over its state to someone else. So I manually programmed this specific application to give it about 40 seconds to hand over its state from point A to point B, which is more than enough time. Probably only need, realistically, more like 10 seconds in order to do it. Once that container is shut down, Kubernetes will then replace it with the updated version using the new Docker image tag that we had before. And then once that container boots up and its liveness check passes, meaning that Kubernetes is able to tell the application started correctly, it'll move on to replacing the next one of the replicas inside the cluster somewhere. And so you can see we'll go ahead and gradually, one by one, replace all of the nodes for this service until they're all running this specific version of the Docker image that I want. Now, the methodology that we're going to use for doing these live deployments is that all applications that use AkkaNET will be deployed as stateful sets, since state is fundamental to how AkkaNET Cluster works and essential for building these real-time applications we're looking to develop. All internal AkkaNET Cluster functionality will be exposed as a cluster IP service, otherwise known as a headless service in Kubernetes. And all external functionality can be exposed as a load balancer or an ingress service, which allows you to go ahead and punch a hole to the external network and let traffic in. And petabridge.command, which we didn't get a chance to talk about today, we'll use that for some node exits. And then deployments and rollbacks, or basically doing upgrades or anything else, are always done by changing the Docker image tag. Now, I'm going to skip that real quick. Now, I'm going to do a little bit of a demo here before I take some questions. And by the way, I'll be available right outside room 5 if you have questions you want to ask one-on-one. But this URL on screen here will take you to a set of step-by-step tutorials we created for learning how to work with AkkaNET Cluster, Kubernetes, Docker, step by step. So it takes about a couple days to do, maybe, depends on how fast you are. But I would go ahead and recommend following up with that if you want to learn how to use all these tools one step at a time. We just published this on May 30th, so it's brand new. Now, what I wanted to show real briefly before we depart ways here is what I have on screen right here is the output from the Kubernetes command line interface called kubectl. In fact, you know what I'll do? I'll clear my screen real quick. I'm going to go ahead and get all the resources inside my Kubernetes namespace I set up on Azure Kubernetes Service. And this would be a bad time for the internet to go down, but I don't think it will. Nope, I should be good. All right, there we go. I just got a list of all my services back that are running inside my Kubernetes cluster. Apparently, my Jaeger node, Jaeger's a distributed tracing tool, ran out of memory and got evicted by Kubernetes. So we'll go ahead and pour one out for Jaeger a little bit later. But my AkkaNET cluster is just fine. I have a bunch of nodes that are still running, and I have about 2 copies of each. What you'll also notice is the set of services that I have running inside Kubernetes right here. Some of them are publicly available, my 3 load balancer services, and they have external IPs that are open to the internet created by the Azure Kubernetes service. So if I go, for instance, to this IP address, 40.74.248.10, if I go and pull that up, I believe that is my application right here that's doing this. This application is basically a fake stock market, is what's going on. And I'm getting real-time price and volume notifications. So yeah, there you go. So we get new price notifications about every 10 seconds. We batch them inside the system. So you can see my web app is doing this. To give you an example that I'm not totally full of it here, I'm going to do a live deployment for one of our stateful nodes that produces this data. And you'll see that the stream of data we receive here does not get interrupted. So I'm going to do that by going to Azure Pipelines here. And I'm going to grab my trade processor. My trade processor is the node that's actually running what's called the order book system, matching buy trades and sell trades together in order to produce matches, essentially. I'm going to go ahead and do a rollback to a previous version of my Docker container. And this is going to run that kubectl command under the covers here. So I'm going to pull this up. Actually, you know what? I need to create a new release. My bad. Let me do that real quick. Do create release. I'm going to go ahead and pick my deployment step, deploy to Kate's. I'm going to go ahead and grab the version I want to deploy. I'll do 0.2. And I'm going to go ahead and kick that off. Now, this is a manual release, so I have to go ahead and check a button, letting Azure Pipelines know that I'm not insane. I'm going to go ahead and do that here. Let's see, let me get rid of that. Click deploy. There we go. So that should run any minute. Let's see. What do you say? Oh, I need to scroll down and confirm it. Oh, there you go. Thank you. See, we've got some experienced Azure Pipelines users in the audience, I see. All right. Thank you. All right, so that's queued up for deployment. And this deployment's very fast. All we're doing is telling Kubernetes to change the version of the Docker image that we're using. All right. In progress. Hooray. All right, and that should be done in a second here. Okay, looks like it's finished. Good. Now, if I go to kubectl and I go ahead and I say get all again, what we should see is some of the pods for that trader service should be getting swapped out now. All right, here we go. So take a look at this. We are in a container creating state here. This means that the old version of that pod was already terminated by Kubernetes and is now being recreated in place. And you'll see in a moment here, the lifespan of this node is already set to 6 seconds. The other node's been active for an hour, meaning that one hasn't been touched yet by Kubernetes. If I go and run my query again here, let me do that real fast. All right. If I do that, you'll notice both of these nodes have now been replaced. So they're both about 30 seconds old. And if I go back to my screen here, my Akka CQRS pricing system, I should go ahead and see another price update in a matter of seconds here. Just a moment. There we go. Got some more pricing information going in. The reason why that was able to work is one of the order book nodes, when it shut down, handed off its state to the next order book node. And then when that node had to shut down, it handed it back to the new node that just got upgraded. So they kind of ping-ponged their state back and forth and persisted everything to MongoDB under the covers. So that's it for my presentation today. I'll go ahead and pull up the URL one more time here. If you want to learn how to do this step by step, please go here. Otherwise, thank you very much for attending my talk today, and I'd love to talk to some of you outside if you have questions. Thank you very much.